So determining chemical formulas from experimental data. We mentioned types of formulas, and empirical formula is one that we mentioned. An empirical formula is derived from experimentation, and it gives us the simplest ratio of atoms of each element, not the actual number of atoms in a molecule. But elemental analysis can give us masses of the individual elements in a compound, either by decomposing the compound we can find this out, or by reacting compounds to form new compounds we can figure out what the masses of the elements are. So that's one source of, or one set of data that can give us enough information to calculate an empirical formula. We could also calculate it from the percent composition. Finding the empirical formula is not really difficult. It's just a series of steps, and it's easy to get lost and forget what step you're on and where you're going. So here's the list of things that we're going to do. First, we write down the masses of each element present. Now, if you're given a percentage instead of a mass, all you have to do is say, well, let's assume we have a 100-gram sample, and then the percentage is the same as the mass. So if they give you a percent, 5% carbon, just change the percent to gram, and you're good to go. But you need masses, mass of each element. Then we're going to find the moles of elements. We'll convert those masses to moles using the molar mass of each element, because the formula deals in ratios of numbers of atoms or moles of atoms. So we have to get to moles. Now this is where I'm not too keen on the specific directions they give you in the textbook. Is to write a pseudo formula using the number of moles of each element as subscripts. Well, you can do that. Divide all the subscripts in the formula by the smallest subscript. If the result is within 0.1 of a whole number, you can round to the whole number. If it's not, so like if we come up with a ratio of 2.9, okay, 2.9 is 0.1 away from 3, and so we can round it to 3. If we get 2.8, that's 0.2 from the nearest whole number. You can't round it. If you can't round them to get whole numbers, then you're going to have to multiply all the subscripts by the same whole number to get whole number subscripts. And this is like instructions of a board game. I'm reading them to you and you're like, right? We'll get through this. We'll do an example. Hopefully it'll make more sense. You can do this blindly by trying 2. Oh, that didn't work. I'll try 3. Oh, it didn't work. I'll try 4. Or you can recognize that fractions are related. Fractions and decimals are related. This is 1/5. This is a 1/4, a 1/3, etc. And so if you see numbers real close to these, that gives you a clue as to what number to multiply it by. Okay, enough with the instructions. Let's play the game. It's a fun game. So here we have a sample of an unknown compound, and we're given percentages of zinc, phosphorus, and oxygen. They're asking us, what's the empirical formula? What we're trying to do to find the empirical formula is we need whole number ratios, moles of zinc to moles of phosphorus to moles of oxygen. So we start with masses. These are percentages, but if we had a 100-gram sample, it would be 75.84 grams of zinc. So that's what we'll do. So 75.84 grams. Write the element symbols in here. So we have that many grams of zinc, and we have 97 grams of phosphorus, and we have 0.193 grams of oxygen. Masses of elements, that's where we start. We're going to convert those to moles. So we're going to multiply by the molar mass. We want moles of zinc, and we're dividing by grams of zinc. Periodic table says 65.39. Here we're going to have moles of phosphorus divided by grams of phosphorus. It's 30.97. And moles of oxygen to grams of oxygen, 16. Okay, so these units are canceling out, and we're going to get moles of these different elements. 75.84 divided by 65.39. When you're doing empirical formulas, you definitely want to carry extra significant figures. You do not want to over-round. Rounding errors here will give you the wrong formula. All the significant digit stuff ends up disappearing at the end, so you don't even have to keep track of it at all. But just carry some extras. Here we've got 4 and everything, so I'm going to write down 6 just to be safe. Don't switch on me there. 1.1598. That's not 6. 1. Wow, that was... well, maybe I'll have room. Maybe I won't. We'll find out. I'm going to start over there. I'm zooming in on this little tiny thing, and it makes me crazy sometimes. 1.15981. And that's moles of zinc. 23.97 divided by 30.97. This guy is 0.773975 moles of phosphorus. And the oxygen is 0.0120625 moles of oxygen. If you want to do the whole pseudo formula like your book shows you, you go right ahead. What I do now is I look at these numbers and I say, okay, I need whole number ratios. Which one of them is the smallest? It's the moles of oxygen, right? This is the smallest number. We're going to divide everything by the smallest number. This one's going to end up being 1. Like, do I even have to bother writing all that out? Well, no, you probably don't. So that's going to come out to exactly 1. The others will come out to something greater than 1. And that's what we're trying to do, is we're trying to get away from these small little numbers here. I'm getting 64. Anybody else getting 64? That just seems like a really, really weird number. That's what it is. 64.637. I'm having this vague feeling that there was a problem with this problem last year. Because this is not looking good. There are molecules with subscripts like 64, but we don't usually run into them in problems like this. Okay, I'm going to pause and look into this. Okay, I fixed the percentages. I don't know what happened with that problem. Anyway. Okay, so let's kind of speed through what we've already done, but now we have to do it again with the new numbers. So annoying. 50.83% zinc, so 50.83 grams of zinc. And we're going to convert that to moles. Moles of zinc. Yeah, I can't fix it that way. 65. Why can I not remember that number? 0.39 grams of zinc. Calculator. So I'm getting 0.777336. That's moles of zinc. And we've got 16.02 grams of phosphorus. We're multiplying by moles of phosphorus, dividing by its molar mass, 30.97. We're getting 0.517275 and 33.15 grams of oxygen times moles of oxygen over 16 grams of oxygen. Okay, so we convert those to moles, and now we're going to take the smallest number, which now ends up being this one in the middle. We're going to divide each by the smallest. So that means that one of them is always going to have a ratio of 1. The moles of phosphorus atoms to moles of phosphorus atoms is 1 to 1. That is kind of necessary. I'll take this one, divide it by the smallest. All the other numbers are going to be greater than 1. So this one comes out to 4.005. And we'll divide this one and this one comes out to 1.503. Now obviously the one in the middle is a whole number. Can we round this one to a whole number? Yes. Yeah. But can we round the top one to a whole number? No, we can't. So what that means is that we need to multiply all of them by the same number, because we're looking for the ratio. Here our ratio is 1.5 to 1 to 4, but we need these to be whole numbers. And if we multiply one of them by 2 to get a whole number, to keep the ratio the same, we have to do it to all of them. So if we multiply 1.5 by 2, we're going to get 3, aren't we? And this one will multiply by 2, and that's going to give us 2. And this one times 2 will give us 8. These now are the subscripts for our chemical formula. So the empirical formula would be zinc 3, phosphorus 2, oxygen 8. And that's the empirical formula. Any questions? Yes?
Factor out a 2 from the phosphorus and the oxygen?
The question is, can you factor out a 2 from the phosphorus and the oxygen? Well, you could if you're going to put them in parentheses. You're seeing a phosphate in there, right? You could do that. I'll do that up here at the top. Oh, we can't lose the 3 there. We could do that. We generally don't when we're looking at empirical formulas. But that's a very good question. Any other questions? I'm very sorry for the horrible beginning to that question. I don't know what went wrong. The molecular formula. Remember, the molecular formula gives us the actual number of atoms in a molecular formula unit. So it's going to be a multiple of the empirical formula. Could be multiplied by 1, because sometimes they're the same, or it might be some other number. So how do we figure out what the molecular formula is? Well, to do that, we need to know the molar mass of the compound. And this is something that could be obtained by mass spectrometry or something like that. So we need the empirical formula and the molar mass. And so what we do is we find out how many of those empirical formulas fit into the molecular formula. So we take the actual molar mass and divide it by the mass of our empirical formula. And this will almost always give us a nice whole number. If it doesn't give you a whole number in these setup exercises, that means you're calculating something incorrectly. So here's an example. During excessive physical activity, lactic acid, which has a molar mass of 90.08 grams per mole, forms in muscle tissue and is responsible for muscle soreness. The empirical formula of lactic acid is CH2O. Determine the molecular formula. We know that the molecular formula is some multiple of this. We know that the molecular formula weighs this much. So we're going to calculate the mass of this empirical formula and see how many times it goes into this. So the empirical formula mass is 12.01 for that carbon, 2 times the mass of hydrogen, and 16 for the 1 oxygen. And I rolled away from my calculator. .026. So we want to find out how many times this fits into that. So we take 90, and some of you can tell just by looking at this, 90.08 and divide by 30.026. And our calculator says, and it's actually got 4 zeros. 1, 2, 3, 4. They're always going to come out to be really nice numbers here. So this tells us 3. We have to round this to an integer. If you end up with 3.5 or something, you messed up in your calculation somewhere. Try again. So this tells us we take the empirical formula, CH2O, and that's multiplied by 3. There are 3 of them. So usually for a molecular formula, we'll actually multiply it through and say, okay, this must be C3H6O3. And this is not giving us any indication of how those atoms are connected. It's just telling us there's 3 carbon atoms, 6 hydrogen atoms, and 3 oxygen atoms in one molecule of lactic acid. A lot of times they'll combine this question, a question like this, with the previous question. They'll give you a percent composition and a molar mass and ask you to find the molecular formula. And so you just have to do more steps. Any questions? Combustion analysis is one technique for determining formulas of compounds. And this works really well with organic compounds that contain carbon, hydrogen, and oxygen. Because when you burn an organic compound that contains carbon, hydrogen, and oxygen only, you get carbon dioxide and water as your products, always. So, if we know the mass of the products that are made and the composition of the constituent element that's in the product, we can find the amount of the constituent element that was in the original compound. So the carbon will go into CO2, the hydrogen will go into H2O. Oxygen, there's going to be extra oxygen present so that this will combust. And so we don't measure the mass of the oxygen directly, but whatever wasn't carbon and hydrogen must have been oxygen. So we find the oxygen by subtraction. Here's an example of a setup. So here we have a furnace and we have a supply of oxygen. We place a known mass of unknown compound into this furnace and burn it, and the fumes are passed through a series of tubes. This first one is going to absorb the water. We weigh the tube before and after. The difference in mass gives us the amount of water that was given off from this combustion reaction. And then the fumes are also passed through a carbon dioxide absorber. The increase in mass of this tube corresponds to the mass of carbon dioxide that was produced. So vitamin C, here we've got its molar mass, contains carbon, hydrogen, and oxygen. It's found in a lot of natural sources. 1 gram sample gets burned in a combustion apparatus, and we get the following data: the mass of CO2, the mass of water, and we're asked to find the molecular formula of vitamin C. This is not a trivial problem. There's a lot of different things that we have to do, but it's not impossible either. From the mass of CO2, we are going to find the mass of carbon that was in this original 1 gram sample. So we're going to take this mass of carbon dioxide. So this is grams of CO2. And I'm going to find how many grams of CO2 per mole of CO2. So CO2 is 12.01 for the 1 oxygen, plus 2 times 16, molar mass of 44.01. So I'm going to cancel those units. That gives me moles of CO2. How many moles of oxygen would that be? Why? Well, yeah, I see your confusion. Why do we want to know the moles of oxygen? We don't. We want to know the moles of carbon. How many moles of carbon? How many moles of carbon in a mole of CO2? 1, right? And we get that just by looking at this formula, CO2. There's 1 carbon in the CO2. So there's 1 mole of carbon in 1 mole of CO2. So 1, oh no, I can't do that. Okay, so I'm going to find the moles of carbon here, and I'm also going to write down the moles, the grams of carbon. So I've got 1.5 grams of carbon dioxide, and I'm dividing by the molar mass of carbon dioxide, and then it's 1 to 1. And so this is 0.03483 moles of carbon. How do I find the grams of carbon from that? I'll multiply by 12.01, and so that is 0.40934 grams of carbon. So I've got 0.41 grams of water. I want to be dividing by grams of water, multiplying by moles of water. 2 times 1.008 plus 16, 18.016 grams of water per mole. The grams cancel out. How many moles of hydrogen are in a mole of water? 2. 2 moles of hydrogen per 1 mole of water. .41 grams divided by 18.016 times 2. So I've got 0.045515. I'm just carrying extra digits along here. That's the moles of hydrogen. I didn't cancel out all my units. To find grams of hydrogen, what would I do? I'd multiply by the molar mass of hydrogen, 1.008. And so that tells me that there are 0.04588 grams of hydrogen. Now, I figured the moles and the grams of each of these so that we don't have to come back to one of them later. What do we need to find the empirical formula? We need the masses of elements, right? So here I've got the mass of carbon, the mass of hydrogen. How do I find the mass of the oxygen? I subtract both of those from the mass of the original sample. I'm going to do that up here on top. So 1.000 grams of the vitamin C. And I had 0.40934 grams of carbon, and I should put a 0 in there. 0.4588 grams of hydrogen, and that gives me 0.54478 grams of oxygen. Yes, question. Where does the 1 come from? This one up here. That's a good question. Here we're told a 1 gram sample. So it comes from right here. They gave us the mass of the sample. So there's 3 components in it, carbon, hydrogen, and oxygen. Yes, we're subtracting. I forgot to put the sign there. This is subtracting, and that's a 0. I need to reformat this slide because it doesn't leave me enough room to solve the problem. we now have the mass of each of these components. What did we do next after we have the mass to find the empirical formula? We convert the masses to moles. We need moles of each element. We need moles of oxygen and moles of carbon and moles of hydrogen so we can get a mole ratio. I was thinking ahead a little, which, maybe that wasn't a good thing. I was in the process of calculating this. I did need this number, but I thought, as long as I'm calculating this, I'm going to write that down. Otherwise, you could take this number and divide by the molar mass and get back to that number. But we need the moles of we need the moles of oxygen. 0.54478. And yes, I've kind of thrown sig figs out the window a little bit. I'm carrying extras. Moles of oxygen. Each mole weighs 16 grams. So there's our moles of oxygen. And we've got 0.034083 moles of carbon and 0.045515 moles of hydrogen. When you're working out problems like this at home, I recommend using plenty of paper. Just give yourself plenty of space. This is beyond ridiculous, and I'm sorry. Okay, which of these moles is the smallest? It's almost a tie, but the oxygen, right? So this divided by itself is going to give us 1. This one divided by that is also going to give us really close to 1, isn't it? 0.034083. That gives me 1.001 if you round it. And then this one, 0.034049. .3367. So we have a ratio of oxygen to carbon to hydrogen of 1 to 1 to 1.3367. Can we round 1.3367 to 1? No. 0.33 is the decimal equivalent of what fraction? 1/3, right? So if we multiply by 3, we'll probably get a whole number. So multiply by 3. Here I get 4.01. I'm just writing enough digits here, decimal places, to show myself that, yeah, this is within 0.1 of this whole number, so I'm okay to round it. So times 3 is going to work for us. So then we need to multiply this one times 3, and this one times 3. So we want to carry some extra digits, carry plenty of digits around. When we get to the end, they're all going to become whole numbers. So carbon, hydrogen, and oxygen. So carbon would have a subscript of 3, and hydrogen would have a subscript of 4, and oxygen would have a subscript of 3. Now, why did I write them in that order? Because that's the order they were given here. I don't think if you wrote them in a different order down here, I don't think even Mastering Chemistry would have an issue with that. But there's kind of an order implied there. Is that the answer to our question? No. Okay, sometimes we get lost in the forest, right? And we're calculating, we come to an answer, we're like, yay! It's like, yeah, but we're not at grandmother's house yet, okay? We just reached the fork in the path. We have further to go. We are looking for the molecular formula. So we have to find the formula mass, or the empirical mass of this, and divide it into that number and see what we get. Okay, so I'm going to make space. Phew. So this would be 3 times the mass of carbon, 4 times the mass of hydrogen, 3 times the mass of oxygen, I'm getting 88.02. I'm sorry, 88.062. So 176.12 divided by that. And my calculator shows 1.99995. Very definitely close enough to 2. The 2 tells me that I need to multiply all these subscripts by 2. So C6, H8, O6. That's the molecular formula for lactic acid. I'm sorry, vitamin C. Forgot which problem we were doing. That was fun, wasn't it? Yeah, I'm sorry. I'm sorry. That was a mess. It really was.